Welcome to this third and final video presentation on Level 2 acids and bases. The focus on this video presentation is to cover the concepts of strong and weak acids and bases, two terms that often get confused with concentrated and dilute, but actually have specific chemical meaning. This cartoon refers to strong and weak tea, but this is a misconception in chemistry. They are not referring to the strength of the tea at all, but actually to the concentration. This person's tea is not stronger, but it is more concentrated, which is why his sample has a darker colour. This person's tea is not weaker, but is actually more dilute, which is why the colour of the tea is less intense. So we're going to review these terms strong and weak and find out what they really mean in the context of chemistry. The learning outcomes in this presentation are: review common misconceptions with key words, define strong acids and bases, describe the properties of strong acids and bases, define weak acids and bases, describe the properties of weak acids and bases. Pretty straightforward, but we are going to focus on acids given the time factor we have available to us. Let's begin by reviewing a few key words that are a source of common misconception. Firstly, concentrated and dilute. A concentrated solution has a large number of moles of solute dissolved in 1 litre of solvent, whereas a dilute solution has less. So this beaker has more concentrated as there are more particles in the same volume, and this beaker is more dilute. Secondly, dissociate and dissolve. These two terms are very similar. Dissolve is a generic term applied to anything that breaks up and disappears into water. This includes both breaking of intermolecular and/or intramolecular bonds in the substance. Dissociate actually refers to the breaking of intramolecular bonds only, i.e. covalent or ionic bonds, as a substance breaks up in water. So sugar dissolves, but sodium chloride or salt dissociates. Essentially, dissociation is a subset of dissolving. Sugar and sodium chloride both dissolve as bonds are broken as it moves into the solution. Sugar breaks intermolecular bonds, and sodium chloride breaks ionic bonds. But only sodium chloride dissociates, as this involves the breaking of the intramolecular ionic bond. Don't worry if you get these two terms confused. I will accept either term used at this stage. The difference between them is quite subtle. Lastly, strong and weak. A substance that completely breaks up or dissociates is considered strong. If only some of the molecules break up or partly dissociates, then it is considered weak. Examining this concept is the purpose of this presentation. Before we do, there's one more thing to review, and that's 3 properties. The pH of a solution is a measure of the concentration of hydrogen ions. A high concentration of hydrogen ions will result in a low pH. The rate of a chemical reaction between acids and metals or carbonates is related to the concentration of hydrogen ions. A high concentration of hydrogen ions will give a fast reaction rate, and you'll remember this from chemical kinetics. Conductivity of a solution is related to the concentration of the ions dissolved into it, and this is the total ion concentration, not just cations or anions, but both. A high concentration of ions will give a very conductive solution. This is why salty water is a much better conductor than rainwater. So these are the 3 properties that we must compare our strong and weak acids to. Okay, let's start with strong acids and bases. These are the ones that you've had most dealings with so far. Strong acids include hydrochloric acid, nitric acid, and sulfuric acid. Strong bases, your hydroxide compounds of potassium hydroxide, sodium hydroxide, or even calcium hydroxide, which is lime water. The definition of a strong acid or base is one that completely dissociates when dissolved into water. In other words, all bonds get broken. And to show a complete reaction, we use a normal arrow. So if we use hydrochloric acid as our example, we would show the dissolving or dissociation equation like these. and either of these two forms would be fine. And if we looked at a particle model of our hydrochloric acid in solution, it would look like this, with all molecules of HCl having dissociated into ions in solution. In other words, every molecule has had the covalent bond between the hydrogen and the chloride broken. This is complete dissociation for a strong acid. So if the solution is 0.1 molar hydrochloric acid, 0.1 molar of hydronium ions, and 0.1 molar of chloride ions, the total ion concentration in this solution will be 0.2 molar. This is exactly the same for strong bases like potassium hydroxide or sodium hydroxide. They completely dissociate into ions too when dissolved into water, but of course will produce hydroxide ions instead. What then are the properties of strong acids or bases? Again, we're focusing on acids given our time constraints. As a strong acid completely dissociates in water, it will have the highest possible concentration of hydrogen ions present in solution. Therefore, it will have the lowest possible pH value, and this is the same for strong bases, but they will have the highest possible pH due to the high concentration of hydroxide ions. And it will also have the fastest possible reaction rate, because again, reaction rate is related to concentration of hydrogen ions. High concentration, fast reaction rates. As a strong acid or base completely dissociates, it will have the highest possible concentration of dissolved ions in total. Therefore, it will have the highest possible conductivity in solution and will be the greatest conductor if exposed to an electrical current. So, using our 0.1 molar hydrochloric acid, we would have a very low pH value of 1.0, react very fast with metals or carbonates, and will have the highest conductivity with an electric current. Okay, now let's look at weak acids and bases, again focusing on the weak acids in particular. Some weak acids include the hydrogen carbonate or carbonic acid, ethanoic acid, methanoic acid, and the ammonium ion. So we've got 3 molecular species that are weak acids and 1 in this example which is a cation. Weak bases include ammonia and organic amines and the 2 ions bicarbonate and carbonate. So weak bases could be molecular species or ionic species also. A weak base or acid is one that partly dissociates when dissolved into water. It dissolves in an equilibrium reaction. This means that only some of the molecules dissociate and most of them do not. The key with these species is that they react in equilibrium reactions. So we use an equilibrium arrow when we draw the dissociation reaction. Here's an example using ethanoic acid and water. Both of these equation forms are correct, but the second equation is a better representation as it shows the acid-base proton transfer from the ethanoic acid molecule to the water molecule, which is actually what occurs in water. Because this is an equilibrium reaction, there will be an equilibrium expression and an equilibrium constant that goes with it. For ethanoic acid, the value of the equilibrium constant is 1.8 times 10 to the minus 5 at 25 degrees. This is a very small number, which shows that the equilibrium position lies to the right, i.e. towards the reactants, and there is only a very small amount of products present in solution, in this case the dissociated ions. This will have effect on its acidic properties. You should have a look at this diagram now and consider what it's showing you. Notice the number of undissociated molecules present in solution as opposed to the number of dissociated conjugate base anions and hydrogen ions. This is very typical for a weak acid. So what will the properties of a weak acid solution be? Let's use our 0.1 molar ethanoic acid solution as an example, given by this weak acid equilibrium reaction here. In a 0.1 molar ethanoic acid solution, given that it is weak and only partly dissociates, there will be less than 0.1 molar hydrogen ions and 0.1 molar ethanoate ions. Although you might be aware that whatever they are, they will be the same as each other because it dissociates in a 1:1 ratio. And the total ion concentration of these two added together will be some number well less than 0.2. How does this relate to their properties? Well, since the hydronium concentration is less than 0.1, the pH value will be greater than 1. This shows that it is a weak acid. Since the concentration of the hydroniums is less than 0.1, the reaction rate will be slow this time. And since the total concentration of ions is much less than 0.2, the conductivity would be low as well. Also consider the solution is mostly molecules and only some ions, and we know that molecules don't conduct electricity. Let's make some comparisons between a strong and weak acid. Here are some simple summary statements and diagrams. These are worth copying down onto your whisk sheet, and you should consider the diagram and the relative number of undissociated molecules as opposed to dissociated ions for a strong and weak acid. Here is another representation using some generic terminology which is often referred to when using different acids, acids HA and acid HB. HA is a strong acid. All molecules dissociate into H+ ions and A- anions. HB is a weak acid. Some molecules dissociate into H+ ions and B- anions. You should pause the video at this point and study this diagram, as it relates to particle pictures with a simple bar chart showing the relative concentrations of the species in solution. Make a note onto your whisk sheet of what you interpret from these diagrams. Here is another representation that ties together the concepts dilute, concentrated, weak and strong into their four groups. Again, pause this video and interpret what these diagrams represent. What do you think the answers are to these questions? To finish off, here is a sample question that uses that generic terminology for the two acids. If 0.1 moles of HA and HB were dissolved into 1 litre of water, and the pH of HA was measured to be 1.0, and the pH of HB was measured to be 2.0, which is the stronger acid? What do you think the answer is? But most importantly, how would you explain it? What would you write down? Here is a sample answer for you to consider. They are both the same concentration, 0.1 molar, but the pH of HA was lower than the pH of HB, so HA has completely dissociated and HB has only partly dissociated, producing a concentration of hydrogen ions that is lower than 0.1. Therefore, the pH will be higher. This makes HA the stronger acid than HB. Essentially, HA dissociates to a greater extent than HB, releasing a higher concentration of hydrogen ions, therefore a lower pH. You can make this comparison directly because they're both the same number of moles dissolved into 1 litre of water. So what you're looking for is evidence of the amount of dissociation. And that's it. You should pause this video at this point and copy these two summary points down that cover the basic achieved evidence for strong and weak acids. Remember, the same principles apply for bases, except you'll be referring to pH values which are greater than 7. So strong bases produce pH values much closer to 14. Weak bases produce values that are much closer to 7. And that's it. We have finished this topic for chemical reactivity. Well done. You should give yourself a congratulatory pat on the back.